Hello friends, from last two lectures we had discussing about this organic reaction mechanism, and in last two lectures we were already discussing about the carbocation. So we have already done the generation of carbocation and structure of carbocation, then stability of carbocation. So carbocation is a species, it's trigonal planar compound containing a positive charge on carbon. All three bonds are in a one plane and one unhybridized pz orbital which is empty is perpendicular to that plane, means to that three bonds, and the bond angle between two bonds is 120 degrees. So in case of a stability of carbocation, that tertiary carbocation is more stable than secondary and secondary one is more stable than primary. If there is electron releasing room present on carbocation, means if any strong releasing group attached to carbocation, then stability of carbocation is increased, and if electron withdrawing group present on carbocation, then its stability goes on decreasing. Then also if there is a hypoconjugation effect is possible, stability also increases. Like also if there is a resonance possible, means canonical structure possible for that carbocation, then its stability also increases. If there is more the double bond in conjugation, the stability will be more. Then in case of if there is any heteroatom also present adjacent to that carbocation, then that heteroatom can also use this electron pair for the stability of carbocation. Then in case of generation, different ways for the generation by alkyl halides, by diazonium ions, by alcohols, by acyl halides, so many types we have already discussed. Then in case of reactions of carbocation, we have already discussed in our second lecture. Okay, now let's see the applications of this carbocation. In case of application, we are going to see now some important reactions. Main reactions are, and in exam mostly they were asked on this point. So let's see the applications of carbocation. First one is Friedel alkylation. About this we have already discussed in our last lecture. Fc alkylation or Fc acylation. If there is an alkyl group in the compound we are using for the substitution, then means substitution of any alkyl group is there, then it's Fc, means a Friedel alkylation. And if there is any acyl group containing carbonyl compound, then we call it Friedel acylation. Let's see one by one. So in case of Friedel alkylation, the compound we have is benzene ring plus any N-propyl chloride containing a halogen. Halogen attached compound असणार आहे. So benzene ring plus N-propyl chloride in presence of AlClC. AlClC is Levy's acid. Giving a temperature means giving a heat. In presence of a heat, it will give you isopropyl benzene and N-propyl benzene. Means you are getting substitution at second position. म्हणजे हा जो ग्रुप आहे याच्या एकतर सेकंड पोझिशनला सबस्टिट्यूशन मिळतो किंवा फर्स्ट पोझिशनला इथे सबस्टिट्यूट होतो, बरोबर. सो दिस टू प्रोडक्ट्स आर पॉसिबल, बट the 60% is isopropyl benzene. So why this compound or why this product is more stable or yield is more? Let's see its mechanism. Simply it's a substitution reaction. If there is alkylation, we are looking for alkylation, then alkyl group will be substituted on benzene ring. We have this N-propyl chloride in presence of AlClC. AlClC is a Levy's acid. It will take a pair of electrons. So it will attack on this and abstract one chlorine. Now you will get this type of sequence: CH3, CH2, CH2, AlCl4. As this AlClC have taken this Pal, now it's become AlCl4. Electron जैसे accept केल्यात म्हटल्यावर त्याच्यात निगेटिव्ह चार्ज आला, याने इलेक्ट्रॉन डोनेट केल्यावर त्याच्यात पॉझिटिव्ह चार्ज आला. So in this species, you can see now generation of carbocation takes place, right? Generation of carbocation takes place CH2 plus. But this carbocation is primary carbocation. This is like a salt conjugate, okay? There is no bond between this CH2 and AlCl4. So it is an ionic structure, so it is positively charged CH2 and negatively charged AlCl4. So this carbocation is a primary carbocation. Why? Because it's only attached to one CH2, right? So if there is any possibility of rearrangement in this carbocation or any carbocation, if there is a possibility from primary to secondary or secondary to tertiary, then do it. You can transfer this hydrogen on this carbon, so you will get positive charge on this carbon, right? As per this 1-2 shift, hydride shift, we are going to do 1-2 hydride shift. After shifting, the positive charge will be on this carbon, and now this carbocation is secondary carbocation. As secondary carbocation is more stable, the product from this carbocation will be more, right? Now this carbocation, as benzene ring is electron rich compound, the rearrangement or substitution of this positively charged species takes place on this benzene. Okay, and there is also again rearrangement and stability or regeneration of aromatic structure will be there. So you can see or study more deeply in mechanism. Just for in this topic, rearrangement of this carbocation is important. So in Friedel alkylation, we are going to substitute secondary carbocation for this, that is n-propyl chloride. The most stable one is secondary carbocation, and we are going to substitute this secondary carbocation on benzene, and the final product is isopropyl benzene. This will be a final product and not from this primary carbocation. So you are getting two products, one from this primary carbocation, which one is this one, n-propyl benzene. If this CH2 substitute on benzene, then you will get n-propyl benzene. If the secondary carbocation, if substitute on benzene, then you will get isopropyl benzene, and this one is more stable. Let's see the Friedel acylation. Okay. Now in case of acylation, you are just going to substitute any acyl group on benzene. In case of alkylation, you are going to substitute any alkyl group on benzene. Just see, in case of alkylation, if you have confused about mechanism and they have asked any reaction in paper, then just do this. Any halide group present on this, any alkyl group or acyl group, just break this bond and whole group, but just see for the carbocation, if there is possibility of any stable carbocation, then much more stable carbocation will be substituted. Just break this bond and substitute the CH2 or any alkyl group on the benzene group, like this. Okay. Then in case of Friedel acylation, again the reaction conditions are same. Benzene, then we have now acyl compound, that is acetyl chloride, and we are reacting with AlCl3. Now you will get a substituted compound. Just as the last, you have to break this bond for the final product directly. You have to break this bond and just substitute this carbonyl compound on the benzene ring. Okay, COCH3, CS, substitution of COCH3 on benzene ring. I'm saying substitution, not addition or not elimination. Okay, just substitution. Substitution means you have to just substitute that compound, this group on the benzene ring with hydrogen. Means you're losing one hydrogen atom and substituting in place of hydrogen any group, that is any acyl group or alkyl group. So see, in first step, same reaction. RCOCl plus AlCl3. AlCl3 is a Lewis acid. It will extract this chlorine, and you will get like this. If this chlorine getting out, then electron will be shifted here, and you will get AlCl4 minus, right? AlCl4 minus, and now carbon containing a positive charge. Now, this means acylium ion. So this acylium ion RCO, okay, and carbon having a positive charge. To stabilize this, there may be resonating structures. So electron will shift here, and you will get this type of structure. But for the substitution, this carbocation will attack on benzene ring. So in second step, addition of acylium ion to the aromatic ring generates intermediate arenium cation. So you have to substitute this carbocation on benzene ring. So addition of acylium ion means this, addition of acylium ion to aromatic ring. to aromatic ring, generates an intermediate arenium cation. Arenium cation means arene means benzene containing a positive charge. Arenium cation, which is resonance stabilized. Means as per the last picture we have already discussed that positive charge is stabilized by resonating structures, means canonical structures. So this positive charge present on benzene may be stabilized by different canonical structures. Stability or canonical structure means that positive charge is equally neutralized or equally uh, um, distributed over the whole ring. Okay. So let's see if this CO means carbonyl means acylation cation substituted at this position or this position, then that electrons will make a these electrons will make a new bond. Suppose this electrons attack here and make a new bond between this carbon and this carbon, then there is a positive charge on this carbon, right? Because these electrons are using we are using for making this bond, so there will here will be a positive charge. Just see, just I rotate the structure. If here is a positive charge, then to stabilize this positive charge, this electron in second resonating structure, this electron will shift here, and here will be a double bond, and positive charge will come at this position, right? To stabilize this positive charge, again this electron will shift here, double bond formation, and the positive charge will be here. Again in next step, then again you will get a same structure. Okay. So we are getting three canonical structures. See, these two structures are somewhat same, right? Okay. Then in third step, as now we have this type of structure, means we have this adenine cation, but it is not stabilized. Why? Because firstly we have a benzene ring which is the aromatic system, and we break the aromaticity of that system by substituting this compound. Now to regenerate the aromaticity or for the stability of that phenyl ring, this hydrogen atom will loses hydrogen means proton will loses by giving its electron again as per this, and regeneration or regeneration of aromaticity, or we will get again a phenyl ring, and final product is byproducts are HCl and AlCl3, right? As we have AlCl4, we will get HCl and AlCl3. So in case of Friedel acylation, we are just doing substitution of any acyl group on a phenyl ring. Now the intermediate in Friedel acylation and Friedel alkylation are the carbocation, right? The next reaction is Wagner-Meerwein rearrangement. In Wagner-Meerwein rearrangement, the Wagner-Meerwein rearrangements are common in many reactions involving carbocation as intermediate. For example, nucleophilic displacements occur by SN1 mechanism. Generally, what we are discussing up to now, that secondary, if there is a primary carbocation, then it will rearrange to secondary. If there is secondary, then it will rearrange to tertiary, or possibility primary to tertiary. मोर स्टेबल जो काही कार्बोकेटन असेल त्याच्यामध्ये तो रिअरेंज व्हायला लागणार आहे. सो दिस mechanism actually explained by Wagner-Meerwein. So it is a Wagner-Meerwein rearrangement. See, now we have neopentyl iodide. If we have this type of compound, पहिल्यांदा काय करायचं, हॅलोजन दिसला म्हणजे काय करणार आहे, हा बॉन्ड ब्रेक होणार आहे. बिकॉज हॅलोजन इज मोर इलेक्ट्रोनिगेटिव्ह देन कार्बन. व्हेन इट ब्रेक्स म्हणजे हा जो बॉन्ड ब्रेक होणार तेव्हा काय करणार, इलेक्ट्रॉन घेऊन बाहेर पडणार आहे. सो इट विल बी अ iodine minus means I minus and CH2 plus. So generation of carbocation takes place. Now we have this primary carbocation. You can see here carbon is attached to only one compound other than hydrogen. So this is the primary carbocation. Now see, there is any stability or possibility for the formation of another secondary or tertiary carbocation. Then this, if this compound means the CH3 rearranges to this carbocation, म्हणजे आपण काय करतो आता अल्किल शिफ्ट करतोय, राईट. जेव्हा हायड्रोजन शिफ्ट करतो तेव्हा म्हणतो हायड्राइड शिफ्ट, 1 to हायड्राइड शिफ्ट. जेव्हा एखादा ग्रुप शिफ्ट करतो अल्किल ग्रुप त्या 1 to alkyl shift. So we are doing this alkyl shift, 1 to alkyl shift. The CH3 group we are going to shift from this position to this carbocation. So afterward you will get positive charge on this carbon, right? Now see, this carbon is now tertiary carbocation. Why? Because this carbon is attached to 1, 2 and 3 different groups. So we are getting tertiary carbocation, and tertiary carbocation is more stable than primary carbocation. So finally the product you are getting from this tertiary carbocation and not from directly from primary carbocation. Okay. So after rearrangement from this tertiary carbocation you will get a alcohol. H2 ऍड केल्यानंतर काय होणार आहे, OH पॉझिटिव्ह चार्ज आहे, H2 काय असणार आहे H प्लस OH मायनस. सो OH मायनस जो आहे त्याच्यावरती अटॅक करेल and you will get a 2-methyl butanol. Okay, so this rearrangement is called Wagner-Meerwein rearrangement. The first step in this rearrangement reaction, carbocation is formed, and where loss of leaving group occurs, means after the loss of leaving group you will get a formation of carbocation, and for instance rearranges to a more stable carbocation, and finally you will get product from this more stable carbocation. Okay, this is enough for this picture. In next picture we will see remaining reactions. Please study well. Thank you.